happens is if we are basically talking about the electromagnetic theory, there are you know certain topics that needs to be very clear. Of course, your vector calculus needs to be clear, because when we are talking about something like electric charge, let's say, that would be a scalar. But when we go into the field, we need to know in which direction the field is and so on. So that's why that's a vector. Apart from that, there are certain laws which are very important, and all these laws are there included in this list. So if we just look into the basic overview of the electromagnetic theory, this more or less revolves in this. So you can be in any level of your education and learning physics. If you study electromagnetic theory, these things are more or less there. Okay, it's been there for a very very long time. Maxwell, the final one, you can see final topic, Maxwell's equation. There's a lot of contribution here, in the sense that he compiled all the laws that will actually combine and give me a clear idea of electric field and magnetic field. So Gauss's law, uh, if we look into the Ampere's law, into the Faraday's law, okay. So these are the three laws based on which the entire electromagnetic theory is built. And if we just think about charges, they can be either static or moving. Okay, so what we're going to do now is we're going to start with electric charge and field, and we're going to talk about point charge, dipoles and all, and what are the formulas associated with them. Okay, so as I said, you get a lot of books for this. Griffith is obviously widely followed, but if you want to follow an Indian author, it's K.K. Tiwari. Apart from that, the class 12 syllabus also has these topics. The basics are very clear from there. So electromagnetic theory revolves around four laws, okay, and each of these laws we are going to discuss as we keep on moving around with this topic. Okay, so each of these four laws we are going to discuss. But before that, we need to make our basics clear. So the four laws that electromagnetic theory is based on is Gauss's law in electrostatics, very popular. Get different kinds of numerical problems on this as well. All these four laws, the numerical problems more or less will be based on this. Secondly, we have got Gauss's law in magnetostatics. Third, we have got the Faraday's law, and fourth, we have got the modified Ampere's law. So initially, it was Ampere's circuital law. Maxwell, modified this based on the idea that there can be a flow of charge or current, which is called the conduction current. Okay, and apart from that, the current may be because of the electric field, that is the displacement current. So both of them combined will give you the modified Ampere's law. But anyway, we are going to discuss that later. But you can see here, this is electrostatics, this is magnetostatics. Faraday's law is connecting electric field and magnetic field. Okay, and the modified Ampere's law is also something which is dealing with the current. Okay, electrostatics. So all these laws combined will actually talk about the electric and the magnetic field together, and that's why it is called electromagnetic theory. So to begin with, if we think about charge, this charge can be either static or it can be moving. Now, if it is more or less static, that means it is not moving. The physics for this is different. Okay, and if it starts moving, the physics will again be different, because if you're considering a static charge, and if you want to displace it from its position, you have to bring in another charge. Okay, and this is more or less will be moved. But if you consider a moving charge, you don't need to bring in another charge. Of course, another charge can change its dynamics, its movement and directions and so on. But if we bring in a magnetic field, this moving charge is going to get affected. So when we are talking about static charge, mostly we are going to talk about the terms like electric field, electric force, and so on. And when we are going to talk about the dynamic charge, we are going to talk about the moving charges, which obviously gives me current. And this current will actually be affected by the magnetic field. In fact, this current itself will give rise to a magnetic field. So this simple, concept, which was actually done by Oersted, okay, long back in the 1800s, has proved that electric field and magnetic field are connected. So what happens is, in general, if you are basically having, let's say, a long current carrying conductor, okay, and let's say we have got a charge which is moving, okay, that means it's constituting a current. Okay, Because if we go by the definition of current, I is nothing but rate of flow of charge, dq by dt, if you take the differentiation concept. So this is the rate of flow of charge. So what Oyster did was he took this long current carrying conductor and he put a magnet in front of it, and it was observed that the magnet was actually showing some deflection. That means this current carrying conductor is generating a magnetic field which is perpendicular to the axis along which the current is flowing. So the unit for this was obviously coulomb. Okay, and if you look into the definition of electric charge, it is the property, you can say. Okay, if you consider any kind of material and it has got, let's say, some charge flowing. Let's say it's a conductor and I am applying some potential to it. Okay, the charge will definitely flow. So if we just go into more of basics here, I can have a conductor, maybe this is a copper wire. Okay, and I can actually connect an emitter to it, and then I can also have a battery connected to it, right? So battery will always be one positive and one negative, so a bit of circuits and all that we need to be clear about. So this is my emitter. So if we are basically allowing a current to flow, because this is a potential we are applying, we're applying a positive potential and negative potential. So that means we are going to have a flow of charge. So if we, let's say, have a charge, and we know a charge, or let's say an electron, is a negative, right? So the electrons will always be attracted towards the positive end, and it will be away from the negative end. So if you talk about the flow of electron in this particular circuit example, this is my flow of electron is negative, so it's going to flow from positive to negative. So this current that we have because of the flow of electrons, okay, is called electronic current. That's not the conventional current that we are actually concerned about. Okay, this is very important. Electronic current, these concepts are clear, then later on it will be more easy to get the grip of things. So this is my electronic current. But what happens in conduction current is, let's denote it by I, it will flow in a direction opposite to the flow of electrons. That's what we have read even in our lower classes, right? So this I that we have is actually called the conduction current. This is conduction current. Now the question is, why should the conduction current be considered opposite to the flow of electron? First of all, it's a convention that we usually follow, and there is a very important logic here, that whenever something flows, it will always flow from the higher potential towards the lower potential. So the positive charges are always considered to be at a higher potential, and the negative end is always considered to be at a lower potential. If we have a gas flowing from a empty chamber, oh sorry, from a filled chamber to an empty chamber, that will actually be nothing but flowing from higher potential to lower potential. So here also we're going from the positive to the negative, so it's higher potential to lower potential, and that's why this gives rise to the conduction current. Okay, so that's important. So once these things are clear, we can actually go to the different ideas of this. First thing is, what is electric charge? Obviously I'm not going to write it down, but we should know the definition. It's definitely a property of matter. Okay, and what happens is, it will actually produce a field of its own. It will produce a field of its own. And what we have here is, a magnetic and electric field which will actually be experienced because of these charges, right? That's important. We should also understand something which is there, equipotential surface and all, that is important. If we're basically having a positive charge, as I said just now, and if we are having a negative charge, we know that the charges will obviously flow from the positive to the negative. So we basically have the, not the charge, sorry, the field will be from positive to the negative. Okay, if we are connecting it to a circuit, then the current will flow in this direction. So if the positive charge is there, it will definitely create a field of its own, and this direction of this field would be from positive to the negative. So these are my lines of force. So there are certain properties of these lines of force which we are also going to study. Like for example, if it comes here in this particular position, it's going to contract longitudinally and so on. Okay, so this is the direction of the electric field that we have. Okay, so what happens is, if we are putting up any charge here, let's say I'm placing another charge here, this charge is going to experience a force because of this set. On the other hand, If this is, let's say, E plus, that means it's, let's say, charge of 1.9 into 10 to the power minus 19 coulomb, and this is E minus 1.6 into 10 to the power minus 19 coulomb, but negative. They are equal and opposite, as a result of which it will actually constitute a dipole. So we already know about the concept of dipole from magnets. Electric field also, we can actually talk about dipoles. On the other hand, it's not mandatory that it will always be a positive or a negative charge combination. It can be two positive charges as well. Obviously, they won't constitute a dipole. That's not a dipole. This is a dipole. Okay, this is not a dipole because it's the same charge, positive and positive. Now, in this case, how will the free lines of force behave? It will not come very close because it's repelling, right? So as the lines of force come closer, it's going to deflect further. So these are the, nature of the lines of force when we are having two positive charges. So here also it's going to go. No, they are obviously not going to cross each other. The diagram is fundamentally wrong if I draw it that way. It's going to be like this, okay, and it's going to move away. So definitely, if you're basically having a positive charge and a negative charge, you are not going to have a region where there will be no field. There is no field existing in this region. Similarly, for a dipole, for a positive positive charge combination, there won't be a field, but it will be actually a larger portion of the space in between these two. Okay. So that's the idea behind electric charges and how we place them to actually have different kinds of effects. That's very important. Okay. On the other hand, we do have the idea of conductors and insulators, so we are definitely going to use them. Okay. So these charges that we actually have actually has got certain properties which are very important. Okay. Since we are talking only about the basics, so this is the first class for basics, so I think this will help. Properties are, this is something similar which you might have come across a lot of times. I'm not going to explain all the properties together, but the first thing is additivity. Okay, additivity of charges. Okay, so that means, if we basically have a system and we have got charges here, q1, q2, q3, and someone asked me to find out the total charge. It's very simple. We just add up all the separate charges and find out the total charge and so on, right? So that's the idea behind additivity. Now, why this is a very simple concept, but why we need this is because, there might be numerical tricky problems around this. So if the concept is clear, we can definitely use that idea. Okay. The second is, we are talking about the conservation of charge. Okay, the second topic is, or the second property is, conservation of charge. So if you're basically having an isolated system, the term is very important. We are talking about an isolated system. Isolated. What do you mean by isolated? So, in its true sense, nothing can be so much isolated that there will be any kind of loss. Okay, it has to be a very perfect system to be an isolated system. But in general, we are basically considering a conservation of charge. Let's say this is a box, okay, and we have a charge q1 here, q2 here, and q3 here. Okay, and after some time, this is an isolated system, so there is no escape. The charges cannot come out. In place of q1, we have got q3. In place of q2, it's there, and in place of q3, we have got q1. So q3 and q1 is interchanged their position. But if we just look into the total charge, this will be q, which is q1 plus q2 plus q3, and this will also remain as q1 plus q2 plus q3. So even if the position of the charges changes in the isolated system, the total charge will always remain the same. So what happens is, maybe certain numerical, we are getting a isolated charge system where we have one charge as 1 coulomb, 2 coulomb, 3 coulomb, and after some time the charges becomes, let's say, 4 coulomb and 1 coulomb. Okay, the question is, what will be the third charge? So if it's an isolated system, we can equate them: 1 plus 2 plus 3 plus 3 6. Here it is 4 plus 1 5. So this obviously will be nothing but 1 coulomb charge. So that's the, application of conservation of charge or isolated system. We have studied about conservation laws for so long, so these things are more or less clear. Okay. The final property that I'd like to discuss is very important, and that's quantization of charge. Now this is important. In fact, quantization of charge is something which we already quantization word we have already come across from quantum mechanics. So in charge also there is the idea of conservation, quantization of charge. So if you basically have an electron, the charge of that particular electron is 1.6 into 10 to the power minus 19 coulomb. Now, if you think about fundamental charge, that means the minimum charge that can be existing inside, let's say, in an atom or in a system. Okay, if you're having that, the minimum charge is this. You cannot break it down further. So, if there are two electrons, okay, what you do is, if you want to find out the charge, you just take two and multiply it with 1.6 into 10 to the power minus 19. So any you know system that we have, and if you want to know what is the total charge of that system, okay, this quantization of charge will work. Q is equal to the total number of charges into the charge of each electron, and that's the idea behind quantization, because the charge of the isolated system is more or less fixed. So n can be 1, 2, and so on. So if we take this value of n is equal to 1, 2, and so on, multiply it with charge, we are going to get this quantization of charge concept. Now this is again important. We are going to get a lot of numerical based on this. Okay. Next. So the unit we have already discussed. This is coulomb, but if you're considering the CGS system, that's called stat coulomb. Okay. So we are not going to discuss that right now. So I think units and all are quite clear for you. Okay. Now let's look into a very important law that is important in electrostatics. So it's just like the gravitational field, that if you have two masses, they will kind of attract each other with certain force, and they will be inversely proportional to the square of the distance. So in a similar way, if you're basically having a charge, okay, they are going to be, the force between them is going to be proportional to the product of the charges Q1, Q2, Q2. Please remember the concept. This force that I'm talking about can be repulsive or attractive, but this is directly going to be proportional to Q1 and Q2. How large the charge is, depending on that, it will repel or attract. So I repel, obviously, if it's in opposite, the same nature, positive or negative and negative, but attract when they're in opposite nature, and divided by r square. So that's my distance. So if we just, take the constant of proportionality, that's f is equal to k q1 q2 by r square. So mostly we are going to keep this as k. Obviously we know what is k. K is 1 by 4 by epsilon naught. Okay, and epsilon naught is, permittivity of free space. So if we are saying that this is the permittivity of free space, that means this particular formula that we are using, and we are putting the value of k as 1 by 4 pi epsilon naught, it is only going to work if we are putting it in vacuum or free space. So there can be kind of tricky question that this is placed in certain, field, or maybe in certain medium, which is basically having a dielectric constant. Okay, so that means this permittivity of free space won't be epsilon naught. So if it's only epsilon naught, the value that it has is 9 into 10 to the power 9. Look into the unit here, k is here, so you can take this force as newton, take it here, this is meter square, coulomb square. So if you look into the conventions, okay, or dimensional correctness, this must have the unit of newton meter square per coulomb square. So that's my value for k. But as I said, it's very important that this epsilon naught should not be misread here. It's not that always it will be epsilon naught. Okay, so this is uh, permittivity of free space. Free space. So it should be in a vacuum. That's fine. You can use this. But if the system is not in vacuum, then we have to use the idea of relative permittivity. So relative permittivity is nothing but, epsilon, the total permittivity, divided by the permittivity in free space. Okay, so let's say I want to replace this. Okay, so So I want to replace this epsilon naught. If we have to know what is the total permittivity, so I can just write it down as epsilon naught is equal to epsilon by epsilon r. So if there are questions based on this, these values would be given. Like what is the permittivity of, let's say, a medium, let's say it's water or paper or air. Okay, the air permittivity is very close to 8.85 into 10 to the power minus 12, which is the permittivity of free space. Okay, so that's why, even in air also we can consider that thing. But if to move perfect, then that is very important. Okay, so this is my Coulomb's law. But then we have to understand here that this is basically nothing but a vector quantity. Okay, so this is more or less a vector quantity. Okay, so if we basically, one more formula that we can actually just keep it handy. If we just want to find out the permittivity in, you know vacuum, which is this formula for permittivity, force divided by the force in the medium. So you can, take this formula, 1 by 4 pi epsilon naught. Okay, and divide it by 1 by 4 pi epsilon divided by epsilon naught, and so on. Okay, and this ratio for the same system is also going to give you the relative permittivity. You will put in the formula and then check. Okay, epsilon naught will get cancelled, and so on. Epsilon will also get cancelled, and then we can actually only get the epsilon r value. Okay, we'll get epsilon by epsilon naught here if we compare this. Okay, so this is again, a bit tricky, which is important. So this epsilon r is called relative permittivity. This is also important. Let me just note it down so that we call this relative permittivity. So any permittivity that we are talking about is basically nothing but of the medium. Okay, so if someone tells you what is the dielectric constant, that is nothing but this value. Okay, so this epsilon r can also be written as dielectric constant. So in sometimes they won't really mention what is it. Okay, so that's just give me a moment. So the force is more or less a vector quantity, we know it. So it's important to understand that the force might be attractive or repulsive, and the direction plays a very important role. Any kind of questions that comes in from this topic, force between two charges, it's going to be tricky. There are a lot of questions. It can be of a very difficult level as well, such at times. Okay, so let's imagine this. So that's why this concept is very important. Let's imagine this. We have got two charges, q1 and q2. Okay, and they may be a positive or negative. So for this point, this example, let me say this is positive and this is also positive. Okay, on the other hand, let me take another two charge. Let's say it is q3 and q4. Okay, and in this case, we have got this, and let me just take it to be a positive, and this is my negative. Okay, now in both the cases the direction of the force would be different. For example, if q1 and q2 are there, both are positive, they are going to repel each other. That's why the force on q2 due to q1 will be in this direction. So we can write it down as force on 2 due to 1. This is the direction of the force. On the other hand, if you look force on 1 due to 2, it's going to be force on 1 due to 2, and this is also going to be a vector. But Newton's law works here as well. To every action an equal and opposite reaction. So these two forces are equal and opposite to each other, and that's how the conservation law works, right? So F21 is equal to F12. That's always going to be the case. So obviously this example tells me that these forces are more or less direction. A similar thing will also happen when we are considering the two negative charges, right? Or positive and negative charges. So what happens is, if you basically have a negative charge and a positive charge, and they are opposite in nature, they're going to attract now. So this force is going to act in this direction, and we can say that this is the force that we have on 4 due to 3. Okay, this is in this direction, and obviously this would be in this direction. So at times you might get a question on find out the force If you just find one of them, until and unless it's mentioned that you have to show whether they are equal and opposite or not. Okay, so in this case also we can say that F4 3 is equal to F3 4. So these forces are equal and opposite. Oh, that's very important. Okay, so that's why we say that force is usually a vector quantity. So if we just want to write it down more in a more perfect way, we actually want to write it down in a vector form. That means this is the direction in which the force moves, and any direction can more or less be represented by a unit vector. Means its magnitude is going to be 1. Okay, it's not going to affect the value, or it's not going to affect the magnitude of the value because it's 1, but it's going to tell me what is the direction. Most of the times we use the term r cap because if we're considering a three-dimensional picture as well, we can represent it using the r cap. So if we just want to write down the force in its vector form, if you check your book, a vector, it's in bold, or we can actually use this. So this is k, we know what is k, this is q1 q2 by r square. Okay, and then we have got the vector, which is nothing but r cap. But what we are saying here is that, in terms of vector, and direction is also a vector here. So let me just take a mod here. So this is the way that we can actually write down, where r cap is a unit vector, and we know how to find out a unit vector. If we are basically given a vector representation of anything, we can just take it to be, the vector itself divided by the magnitude of that vector, the magnitude of that vector. So this is my unit vector. So many a times you'll see that different books use different kinds of ways to write down this force. So that's why we can also write it down like this. This is k q1 q2 by mod r square into unit vector is nothing but the vector divided by mod of r. Right? You can write down mod of r bar or mod of r. It's implied. So you see the formula changes slightly here. This is q1 q2 divided by, this is r square into r. So now this will become r cubed. In no way it means that the forces are inversely proportional to the cube of the distance. No, that's square of the distance. It's just because we are changing the unit vector into a vector, and that's where this formula comes in, right? So this is r bar. So what additional information does this particular formula gives me? It tells me that if you're basically having a three-dimensional space, it's not always that you're going to work in one-dimensional space. One-dimensional space is something which is convenient, right? For understanding purpose, it's fine. But in reality, mostly it's going to be a three-dimensional space. So that means it's going to have a component along the x-axis. It's going to have a component along the y-axis, and definitely it's going to have a component along the z-axis. Okay, if they say it's a one-dimensional space, just take this. That means it's only xi cap, nothing, no other values. Okay, so whatever value you get here, because you know what is the distance, you know what are the two charges, multiply it with this effect. So maybe I can take an example here as r bar is equal to 2i plus, let's say, 3j plus k. So along the x-axis, y-axis and z-axis, in which direction the impact is more? Of course, along the y-axis, because it's having three times. Okay, so that's how you can see that if you use this formula, this is actually going to have different kinds of application and way to write it down. So that's very important. Okay, so this is our Coulomb's law, and there are different ways of understanding Coulomb's law. uh, there is also this idea of principle of superposition. Okay, so just as we have seen about additivity. Okay, we are not going to go into too much detail of this because I think it's quite simple. If we are basically having a charge, okay, let's say we are basically having a charge uh, q naught, let's say. Okay, and there are different other charges which are acting on this. So maybe this is q naught, and there are other charges around it, q1, q2, q3, and so on. And we can of course take up a coordinate system, and we can find out what is its position. Okay, vector position. vectorial distance. So this is, let's say, r1, this is r2, this is rn, let's say this is r3, this is r2, and so on. So we have their vectorial position, and if we use our vectors, we know this is my charge. So this charge will be acted upon, or it will be affected by this charge. Let's say all of them are positive in this direction away. This will also happen in this direction, q3 again in this direction, and so on. So what happens is, on this charge, these three charges or other charges are getting, putting an impact. It is getting affected. So the total force that actually acts on this charge 0 is on 0 because of the first charge, on 0 because of the second charge, and so on. So what we can do is we can add up all the forces and see. So this is actually called the principle of superposition. It's all vectors here. So if concept of vector one is clear, the other things it won't be difficult. Superposition. This is principle of superposition. So that's it. Okay. Then we can have, different kind of charge distribution. So that is again very important. Let me just write down this here. The topic is charge distribution. So what happens is, this charges that we are actually talking about, it's not always mandatory that they will be uniformly distributed. That is not the case. Okay? On the other hand, we can also think about a system which might be a one-dimensional system, a two-dimensional system, or a three-dimensional system. So in general, when we talk about density, okay, we always have this concept of mass by volume, mass by volume. But then this mass by volume is actually not called density. This is actually called mass density. That's very important concept. So that means whatever is on the numerator, we'll name it in that form. Okay, it is mass density. So in general, if you're basically considering charge distribution, and let's say I'm basically having a linear charge. Okay, maybe let's say I have number one, a charge which is distributed like this. Okay, and let's say I want to find out what is the effect of this charge distribution on a sole charge, which is a q naught placed at certain distance. Okay, let's say that distance is r from the center of this. But then this is a charge distribution. It may be uniform, it may be non-uniform, we don't know. But for now, for convenience, let's say this is having a uniform charge distribution. Okay, so if I know the density, you can find out what is the total mass. Here you can see this. If you know the density, you can find out mass. You can take the density multiplied by volume, and you can know what is the total mass. So that happens only for uniform distribution. So here also, let's say it's a uniform charge distribution. And here, if we talk about this density, we are talking about a one-dimensional space. This is linear charge density. This is linear charge density. Okay. And if we're taking a very small space, let's say dq, for this particular space, the linear charge density, let's say we denote it by lambda. Okay, so mass density was denoted as rho, if you remember. We're just denoting it by lambda, and d lambda because it's a very small space. Okay, so sorry, not d lambda, it's lambda. So we're talking about charge here. So what is the charge we're taking? A very small charge dq divided by, since it's linear, so we're talking only about one dimensional space. So one dimensional means we're talking about length. So linear charge density is charge per unit length. So this is a small charge density of this small area. Now if this is uniformly distributed, then for any region, the charge density will always remain as lambda. So from this we can actually find out what is my total charge. So if I want to find out the total charge, I can simply write it down, dq is equal to lambda dl. Now I can bring in the concept of integration. Dl is a very small length, and if we integrate it, I'll get the total length, and this will give you the total charge integration. Okay, so this is the idea behind linear charge density. In a similar way, we can also find out what is my area charge density, or we also call it as the superficial or the surface charge density. Okay. So in a similar way, we can write it down. This is important. There may be numericals for this also. Surface charge density. So if you look into surface charge density, we usually denote it by sigma, okay, and this will be nothing but surface charge density. So charge density, obviously, so that's dq on top. Whatever is before density, that will be on top. Here it's mass density, mass is on top. Charge, so charge on top, but surface, that means it's area. So we talk about dq by da, right? Sometimes they write it in book ds also, so that is also there. And then finally, so 3, volume charge density. And this is denoted as rho, okay, and rho would be nothing but dq by dv, right? So this is one dimension, two dimension, three dimension. Okay, so these are the different kinds of charge density that we have. Next, let's talk a bit about electric field. Again, questions might be there from this as well. Electric field. How do I define electric field? Obviously, it's basically nothing but the region around the charge in which there will be some kind of force that is getting experienced. Okay, so what happens is if you put a very small test charge, which usually say it's a test charge, small in the sense that it's going to approach the zero value, it's going to be very close to zero coulomb. Whatever force it experiences will actually be nothing but the electric field. So let me now go to the definition here. It's very simple. The electric field would be nothing but the force experienced by a test charge, force per unit charge. Okay, in this particular case, okay, we are going to write it down in terms of limit. So limit q naught tends to 0. It means that this q naught is going to be a very very small charge, and whatever force it experiences, okay, it's a test charge, it will actually represent the electric field. Okay, that's very important. Okay, so the electric field is the force experienced per unit test charge. So this is there. So because of which charge, okay, that is very important. So let's say I've got a charge q1 here, and we have got a charge q naught here. Now the force experience between these two is nothing but this is very small. Okay, small test charge. Now the force that it experiences, okay, if you go by Coulomb's law, is k q1. Let me just write down the magnitude here, divided by r square, whatever is the distance. Now if we look into this formula and check for the electric field is equal to, I won't remove the remote limit because limit is put just to say that it's a very small test charge, obviously mathematically representing, but it would be nothing but f by q naught. So q naught is there, there is a q naught, it will get cancelled. This would be k q1 by r square. Very important formula. A lot of times we do mix up this. Okay, why I'm saying this, because sometimes you might miss on this r square at the denominator. You might remember that this is an r, but that's not r, that's r square for an electric field. If you're talking about potential, in that case it will be r. Okay, so this electric field is f by q naught, which is k q1 by r square. So remember this. Okay, we can also look into the unit of the electric field. Obviously that's quite clear here. Okay, we look into the formula. Unit of the force, unit is newton. This is a test charge, this unit is coulomb. Now one more important concept, why this is a small, why this should approach zero, because I want, what is the field because of q1, I want to measure that. I don't want to measure what is the field because of this q naught. Okay, so that's the reason that we are going to do it. Okay, okay, so that's why if it should be very small so that it does not produce a field of its own, this should be the field only because of this q1. That's why it's a small test charge. In fact, when we are going to do numerical problems, we're going to see that this small test charge is always considered to be positive. Okay, and if this is positive, this is always going to tell me what is the direction of the electric field. If this is positive, this test charge will always be positive, always be positive. So we know that the direction of the electric field will be away, electric field, remember. But if this is, let's say, negative, the electric field is going to be in this direction. So this helps me to remember or understand what will be the direction of the electric field, and that's why the positive charge is always considered as a small test charge.